Alright, so I'm Andrew Nikos, and this is my original work presentation. I got into aerospace engineering ever since I learned about astronauts. They landed on the moon in 1969, and that was really cool to me, and it was a great journey for them, and I've been interested ever since. So it's just a little bit about me. I'm Andrew. Those are some pictures of some things I do. I play lacrosse and indoor soccer. And this year in ISM, I'm studying aerospace engineering. Alright, my quote that has pushed me through this year is ships are safe in their harbor, but that's not what ships are for. One thing that has really been a big thing for me for ISM is getting out of my comfort zone. So I'm going out to interviews, and I have a mentorship now, and those are all things that before this year I've never imagined doing my junior year. And so now I'm going to talk to you about what I've learned so far in my interview assessments, or in my interviews this year with professionals in the world. So for my first interview, I learned that college is very important. This is one of the biggest things that kickstarts your career in whatever field you're trying to go into. And so 3 colleges that I'm looking at that are top 10 in aerospace engineering in the country are Texas A&M, Georgia Tech, and Colorado Boulder. All of these colleges are like I said, very good for aerospace, and I have connections with people there since my dad went to A&M. I have an uncle who lives in Atlanta, and then Colorado that's just one where it looks fun. And then for my second interview, I learned about the financial viability of companies, because this interviewee wasn't exactly an aerospace engineer, more he was like an industrial engineer, where he would engineer the structure of the company, the assets and liabilities, and he noted the importance of financial success with the company. And so what that means is that no matter what a company is trying to do, they are always trying to make money. That is their primary goal. And so no matter what they benefit or what they're selling, that's their goal. They're trying to make money, so they're always going to have some people dedicated to money on the job. And so some facts about the company that he works for, Lockheed Martin, is they spend over $1 billion in labor a year on their F-35 project, and they have 10,000 plus employees from Lockheed Martin itself and the subcontractors that work on the aircraft. And it takes 2 years to produce one single aircraft, even though they have an assembly line, so they're able to sell one once every 4 days. For my third interview, I learned about the design process. And the 3 key points of the design process are the design, construction, and the testing of a product so that you can sell it to a consumer. Alright. And so the first step of the design process is the design phase. And in this phase, you brainstorm and design your product. So in the brainstorming phase, you come up with a concept to fix your problem, as well as rating these problems so that you can come up with a solution. And then once you have figured out what you're brainstorming, what your product is going to be, you make the concept into an engineering feasibility project by using AutoCAD programs and other design programs to make 3D models and design your thing. So this is a little example of brainstorm. If you want to make something that achieves a purpose. So if you want something that goes from point A to point B, you have to decide whether you want a helicopter, an airplane, or a drone, and what's going to do that most effectively to get your product rolling. The second part of the design process, of the design phase, is like I said, the modeling phase, and making 3D models and blueprints and all that, so that your products can actually work. Second big part of the design process that I learned is the construction phase, and efficiency is the key to construction. So one thing that I learned on my interview is about flow and the ease of access Okay, so flow is important in order to reduce travel times between places. So like in the F-35 construction, one thing that they do, which I thought was rather nice, is they have each part go into where it's going to be on the actual plane. So they have the final assembly line at the front, and what they do is they have like the wings on the side that moves into the center. They have the tail coming from the back, and also the front coming from the back, so that they can put it together easily without having to move parts of the product from each spot. Long travel distances, which is more expensive. And also they want ease of access. So employees need to be able to effectively move to their workstations, be able to effectively work on their part in their workstation. So that means is like they want each part to be done in a specific number of hours or days. And so what they do is that they're able to work on this effectively. They need to be able to access each part of what they're working on and each part of like the aircraft. And companies have used an assembly line structure in order to do this effectively. So this is just a picture of the F-35 assembly line. That's the final assembly where they actually have everything together right before they put the paint on. And these are locations of their locations and subcontractors around the world. And so what they do is they have most parts assembled in either Dallas or South Carolina, and then other parts where it would be more effective to assemble elsewhere is what they do. So they have locations in like Brazil, Britain, India, China, and other things where there's access to cheaper labor. The final phase of the design process is the flight test. And the engineers test the concept in order to make sure everything functions okay and it will achieve their goals of the product. So this here's a little video of a flight test. Yes.
On June 28th, NASA's Low-Density Supersonic Accelerator project conducted the first shakeout flight of a new way of testing technologies that will one day be used to land heavier, more massive payloads on the surface of Mars. We used a large 34 million cubic foot scientific balloon to hoist a 7,000-pound test vehicle to an altitude of 120,000 feet. The test vehicle was then released from the balloon, spun up for stability, and a large solid rocket motor accelerated to over 4 times the speed of sound at an altitude of 180,000 feet, a condition very similar to the conditions we see on Mars. Once we reached the correct speed and altitude, we despun the vehicle. And then we got a chance to test our new supersonic inflatable accelerator. Camera lens covers deployed, we see that inflated very uniformly without disturbing the vehicle too much. And now we're seeing previously unreleased high-definition, high-resolution, high-speed video taken during the test. We used the supersonic inflatable accelerator to slow us to something closer to 2.5 times the speed of sound. We used the balloon to help deploy the new supersonic parachute. The balloon is shot out the back of the vehicle at over 200 feet per second, and then we cut the balloon free and it begins to pull the parachute off the back of the vehicle. As the parachute begins to inflate, we see one of the surprising aspects of this test, which is the early onset of tears in the parachute. We see where those tears began, how they propagated, and otherwise how the parachute behaved as it began trying to inflate behind this very blunt object moving 2.5 times the speed of sound, punching a hole in the atmosphere and creating an extremely turbulent, chaotic environment for the parachute to exist in. We now have a data set that we will use to prepare for 2 more tests beginning in June of 2015.
Okay, so as you can see in this test, they try and make their parachute for a drone or other modules that will land on Mars so that they can do research. And so what they found here is that their parachute that they designed doesn't work. So what they're going to have to do is go back to square one in the design phase and start all over. But everything that they do in here is very scientific, it's very precise. They mentioned that the altitude is 180,000 feet. There's no spin on the aircraft. They have the inflatable thing deploy at 2.5 times the speed of sound to accelerate it so that they can reproduce these conditions again very easily and test their new design under the same conditions. And that's one of the key things for the flight test, so that you make sure that your product will work in the environment that you want it to work in. You click on that slide. Thank you. Alright, so after all my interviews, I decided to choose Mr. Bob Thornton as my mentor, and he's a flight test engineer from Bell Helicopter, and he's really helped me a lot so far this year. Like, when I told him about the drone that I was going to make for my final product, he was not only impressed, but he gave me a lot of things to think about, such as like a heat shield for my drone that could help it survive the dangerous conditions that it'll be in. And so far I haven't had many experiences yet, because we've only been doing visits for about around 2 weeks now. The next part of this presentation is my research that I've done this year and what's led me to the product that I'm making for this year. So the first week of school, I researched the EM drive, because I kind of knew about this before I started, but this is a drive created by British scientists that can run in zero gravity without propellant. Now, this is something that before this was made, people would think that this would break the laws of physics. And so actually it doesn't, because what it does is it contracts the air in front of it and expands it behind it, so that it moves through the air without propellant. It uses the air and space in front of it as a propellant, even though it's not a propellant as we would normally see it, like gasoline. Also, the second thing I researched was a blended wing, which is a new plane design that would greatly increase fuel efficiency. This is designed like between NASA and Boeing, which are two very influential businesses in the aerospace field. Also, the third thing I researched, and this is what led me to my actual original work, are drones. These are very useful tools that can assist in camera operations as well as other operations. So the military uses drones to locate enemies in places like Afghanistan, and other people just use it for hobbies. So like they attach a camera to the drone and they just look around with it and have fun with it. So a little more in depth on the EM drive. So far, it's not very effective. It produces like minuscule amounts of energy, like in the microwatts range. And just for reference, one like an average light bulb is like 60 watts. So it's about 1/1000th time as powerful as your average light bulb, which is pretty poor, but it is very promising as well. A little more in depth on the X48, that's a picture of the actual blended wing, and that's not full size. It's a model that they use to test it. And like what makes it more fuel efficient is it's way more aerodynamic, because instead of having a barrel at the center, the actual place where the passengers sit in the cockpit and the pilots and all that isn't in a barrel, it's actually in the wing. And so what got me started on my original work is the Australian firefighters that use the UAV technology to assist them in finding people that in like car crashes or outdoor wildfires, and they only used existing technology to assist them in outdoor fires. And I thought, hey, I can make something that works indoors, and that led me to my firefighting drone. And this is what I began researching for my original work. So for my original work, I made blueprints for the drone that could go into a fire and locate people still trapped inside, and be able to assist firefighters in their rescue. And this builds up to my final product for the year, which is actually going to be the actual drone. And so this is the top view of the drone, and like, you know, there's a camera there. That's the fire extinguisher. It goes from here to here, and then batteries on top of the fire extinguisher, and like, you know, the engines and stuff that will keep it afloat. And then the side views here, and that's the front view. So what I did in order to create these blueprints is first I sketched them out full size of what I thought the drone was going to look like, so I could make sure it was small enough that it could fly through a house, but also big enough that it could carry the weight of the fire extinguisher and camera. And then what I did is I scanned each image in of the hand-drawn pictures, and uploaded them to my computer, where I outlined everything in Photoshop so that everything would look way more nice and neat, and I could label it in legible handwriting. And that's all. Anyone got any questions?